Okay, so it's really great to be here and to talk about DRAM fault tolerance. So I think we all know the importance of the DRAM fault tolerance, and also like due to the very like excellent error correction capability to both random error and the burst error. We all know that the Reed-Solomon code has been widely adopted in practice. So and also I think if you remember from your college days, like every single like a coding theory textbook tell us that the error correction code decoding can only correct up to the half of the minimum distance. It's really kind of bounded, strictly bounded by the code minimum distance. So that is what we all know, and that is what the whole industry has been doing for all the decades. And actually, that is not necessarily true, that the error correction code decoding or DRAM fault tolerance has to be limited by the minimum distance of the code. So actually, like when the coding theory just emerged as a kind of a new research area in about already like almost 7 decades ago, Professor Peter Alias at MIT actually asked the question, that is why not we can go beyond the minimum distance of the ECC. So his motivation is very simple. That is the minimum distance bound ECC decoding actually only search in a very small Euclidean distance space that missing a lot of opportunities to do the error correction. And even like when we can go beyond the minimum distance. So like actually, for example, like we all know that now for DDR5 DIMM, we use 8064 byte, this 8064 byte Reed-Solomon code to protect 64 byte cache line. And if we just use the traditional Reed-Solomon code decoding algorithm, actually they just search of very tiny space in the code space for the error correction. And so motivated by that observation, Professor Peter Alias in 1950s, he proposed this principle they called list decoding, that we can go beyond the minimum distance of the code by searching in a larger space that to capture those missed opportunities to improve the error correction capability. So that is really kind of very beautiful concept and very well justified. But unfortunately, turns out the practical implementation of the list decoding almost impossible. Is that once we go beyond the minimum distance, we don't have a well-established decoding algorithm, and then the computational complexity quickly just become out of control. So we really have no way in the general purpose sense to practically implement this list decoding list decoding strategy, even though that has been very well documented and started in the academia, that there is a huge potential and opportunity to go beyond the minimum distance for the error correction decoding. So then actually at ScaleFlux, what we have done is that we realized actually we figure out a way to practically implement this list decoding principle, and we apply that in our first generation CXL memory controller. And yeah, before we present that, let's very quickly go through like a review what is going on like in the Reed-Solomon code decoding. So the standard way to do the decoding is that we have this 4 steps, and their computational complexity is listed in this table. And clearly, like for memory fault tolerance, we want to take this fully parallel implementation to minimize the latency and to maximize the throughput. But unfortunately, like once we go to the fully parallel implementation, the computational complexity for the second step and the third step very quickly like increase. That make the, even for the standard Reed-Solomon code decoding, that makes the efficient silicon implementation completely non-trivial. And it's actually like in current practice, that the industry tackled this even for the standard decoding algorithm implementation. What the industry has typically done is that we use the code word interleaving instead of protecting 164-byte cache line on its own. We partition the 64-byte cache line into 4 16-byte smaller segments, and then we use the smaller Reed-Solomon code to protect every 16-byte segment. Then we can reduce the implementation complexity, but of course we sacrifice the error correction capability. So that is what is typically done in practice. So now we are ready to introduce our solution. So actually our solution is very simple. Like that is based upon 2 very simple observations. One is that whenever we read a 64-byte data from the DIMM, almost always no more than two DRAM devices will contribute error in that 64-byte cache line read. So that is observation number 1. And the observation number 2, as we discussed earlier, like the computational complexity problem mainly comes from the second step and the third step. And interestingly, that second step and third step, their purpose is to identify the location of the error. And then the last step is just to correct the error. So intuitively, like if we already know the location of the error, then the second step and third step, they will disappear. Then we can much more efficiently implement the decoding. So that is just a two very simple observations. Then based upon that, we are ready to introduce our DRAM-oriented Reed-Solomon list decoding. So the key idea here is that we convert the traditional error correction problem into a set of eraser correction. So here the eraser means we already know the location of the error, but we don't know the value of the error. We simply just need to figure out what is the value of the error. We don't need to figure out the location, all right? So then taking advantage of the observation that is whenever we read 64-byte cache line from the DIMM, only up to 2 devices will contribute error. Then our idea is that, okay, so we exhaustively examine all the possible 2 devices that can contribute error. So then 10 choose 2, we have 45 possible combinations of those 2 devices can contribute error. Then we examine all of them. So this here shows like when we receive like 80-byte data read from a DIMM, and then we feed that data into a 45 parallel eraser decoding, and then we generate 45 Reed-Solomon code word, and then based on the simple search, then we just can nail down which one is the correct code word that we should use. And that is pretty much all the basic idea of our design solution, and that happened to be the first practical implementation of the list decoding concept that has been invented 70 years ago. And so actually you might wonder, like, even though the eraser only decoding, even though that can be much simpler than the normal error decoding, but we have 45 of them. So the complexity might still be a problem. And fortunately, like we have very good engineers, then they can figure out a way to do very elegant arithmetic optimization that we can further push down the implementation complexity. Then we can very efficiently implement those 45 parallel eraser decoding. So so that is the basic idea of this we call the DRAM-oriented Reed-Solomon list decoding. So we leverage the observation that only up to 2 devices can contribute error. We dramatically reduce the search space. We need to search for the correct code word. And then we are very excited about this kind of discovery. And our first application is for the CXL memory. And we know that for CXL memory, like every 64-byte cache line, we need to add 1 to up to 3 bit of metadata. So to our understanding, current practice is that, okay, so then because we need to store like a couple bit of metadata, then I steal 1 byte from the coding redundancy. And then here we only use 15 byte of coding redundancy to protect this 64-byte cache line. And that is what is being done and to our understanding. So clearly this we waste some space, and more importantly, we use 1 byte less of a coding redundancy. So the error DRAM fault tolerance strength sacrifice. So our solution is that we call the zero cost metadata embedding, and we leverage the very strong error correction capability of our list decoding, and then we still use 64 byte plus 16 byte of Reed-Solomon coding redundancy. We don't sacrifice on the error correction capability, and then when we store the data, we simply puncture away the metadata because we can on the fly to reconstruct the punctured metadata without sacrificing the error correction capability. And then over there, like we further enhanced our solution. We call the like metadata aware list decoding. And certainly like to support this feature, the implementation complexity will increase. So then we figure out another further solutions to really combine leveraging our deep understanding of the coding theory and our deep experience on the VLSI algorithm implementation. Then we have a very efficient parallel decoder in support of this metadata aware parallel list decoder. So then we can talk very quickly talk about our evaluation and the implementation. So we know that for any kind of ECC decoding, not only the Reed-Solomon, so for any ECC decoding, the output could be one of those 3 possible output, like a successful decoding, like we successfully reconstruct the data. The second one is detected failure. That means like a decoding fails, but we know the decoder knows the fails. The last one is the most problematic, like the decoder generate a valid but incorrect the code word. The decoder doesn't know. Decoder thought it already correctly correct, but it is not it is a valid code word, but is an incorrect code word. So that is much worse than the second scenario. And so then for this, actually here, this table summarizes the comparison between our solution and the standard Reed-Solomon decoding algorithm. So here, like we use 8064 Reed-Solomon code. So the minimum distance is 17. So the conventional decoding, they can correct up to 8 symbol errors. So we can see like on the left-hand side, like when the error number is less than 8, then everybody is happy. So then we can correct all the errors. But once the error number go beyond 8, so that means like we have one DRAM chip failure, and then we have a second chip contribute errors. In that case, conventional design totally fail. They cannot correct any error. But for our solution, like we can make sure like even up to 12 errors, we can guarantee almost 100% of the error correction. But we still need to kind of play some trade-off between the second detected failure and the third miscorrection. And so then we have already implemented this list decoder in our first generation CXL memory controller, and we already tape it out. And also like the decoding latency is like up sub 5 nanosecond, and the one engine can achieve almost like a 40 gigabyte per second. And actually in our final chip, the decoder only occupy a small percentage of a chip, like a die area, but we can go far beyond the traditional, this traditional standard Reed-Solomon decoding. So yeah, we are very excited about this. After 70 years, when Professor Peter Ellis at MIT proposed this very beautiful concept of the list decoding, we are the first one in the industry to bring this very beautiful concept into the practice to make it work in the silicon, and then to make it work for our this DRAM fault tolerance. Okay, so yeah, in summary, like yeah, we are very fortunate that we catch this wave on this CXL memory and memory controller, and then over the course of the developing our CXL memory controller, we figure out a way to develop to implement this list decoder that achieve the best in class DRAM fault tolerance, way better than anyone else on the really on the market, and that is really leveraging our understanding of the DRAM characteristics, the coding theory, and the VLSI signal processing implementation. So we really hope like we can work together with the industry to continue to push and raise the standard of the DRAM fault tolerance. So yeah, this last one is a call for action, and certainly like once I think one question is that once we're able to achieve much stronger DRAM fault tolerance, how the whole system can take the best advantage or can take the full advantage of this very strong error correction capability to improve the performance and to do like how we can take advantage on different angles. Yeah, so that's end my talk. Thank you very much.
Thank you, Tong.